So you're able to admit people as well, aren't you? Okay.
Okay, so welcome everybody to this last seminar of the GReTA series before our short summer break. We will return in September. And it's my great pleasure to welcome Aleks from the University of Oxford to the series. Aleks, of course, as many of you will know, has a long history of using some techniques also from graph transformation, including various versions of double push-out writing. And of course, in recent years, many of you will have seen his work on picturing quantum processes and in software, sorry. So Aleks, it's a great pleasure to have you here and welcome to GReTA.
Okay, thanks, Nick, and thanks to the other organizers, Raiko and Joan. I think Raiko is stuck in traffic now, but thanks for inviting me. It's nice to be here talking to you. Yeah, so I'm going to talk. Well, the title of my talk is "Picturing Quantum Software," which is a bit of a jive off of "Picturing Quantum Processes," which is a big pink book with a dodo on the cover. Where we try to do as much of quantum theory using pictures or from the point of view of this community using graphs, so using graph theoretic concepts to really compute things related to quantum processes. Okay, so what is quantum software? I mean, this could just be there's a common kind of buzzword forming device now where you just stick quantum in front of something and it makes it cooler. Well, quantum software means basically one of two different things to two different communities of people. I mean, very roughly, it's the code that runs on a quantum computer. So for one particular community, this means quantum algorithms. So there's the kind of famous Shor's factoring algorithm, which was initially the killer app of quantum computing in the 90s because it can break all sorts of cryptographic codes. And Grover search for searching unstructured databases. And these days, there's a lot of other specialist quantum algorithms that you can run on quantum computers. So this is a big field with a lot of people working in it. And basically not at all what I'm going to talk about today. So what I'm going to talk about is the code that makes the code. So this is really talking about compiling quantum software. So you have some kind of high-level description of an algorithm, and you want to translate it down to something that can run efficiently on a quantum machine. Okay, so in addition to just running, being runnable at all, we want to make things run fast, and we want to make sure they run correctly. So optimization and verification are sort of rolled into this idea of quantum compilation. Okay, so if you worked in this area until, let's say, 5 or 6 years ago, a common trolling that you would get is that there's just no quantum computers, so this is kind of pointless. This isn't really the case anymore. There's a lot of big Silicon Valley players actually have quantum computers. You're seeing them in the headlines all the time. And there's lots of startups and academic departments which are really building these things. And you can access them over the cloud, and you can actually run code on quantum computers and get some output. The downside of these is that they're actually very limited. So there's this term that kind of encompasses the things that we have today or in the near future, which is called NISQ, which stands for Noisy Intermediate Scale Quantum. And this generally means devices which don't run for very long before the noise kind of takes over. Where your operations are very noisy, where you don't have much quantum memory, and they have various other kinds of limitations that you have to live with. This is a problem for actually running algorithms on these things, and it's actually a big problem. But it's a nice time to be working in this area of compilation, because if you make little improvements in how you're actually compiling these algorithms, you can all of a sudden your quantum computer is just twice as powerful or something. So you can actually get really big gains from doing this. Okay, so the main thing I will talk about when I talk about quantum code, the sort of low-level code that runs on a quantum computer, is in this language of quantum circuits. So you can think of quantum circuits as a kind of assembly language of quantum computation, where you have this list of basic instructions, and you can think of this as really analogous to classical assembler, where you would have some kind of addition or moving things around in registers and so on. The quantum analog is these quantum circuits. So each of these lines in this instruction corresponds to just some kind of physical operation, or, well, logical or physical operation, but at the lowest level, physical operation that a quantum computer can do. So something could actually, one of these instructions could correspond to apply a microwave to the third qubit for such and such many nanoseconds. So circuits can really describe quite low level operations. So it's really important to be able to optimize these circuits. And the old-fashioned, or you could say the kind of naive way to optimize quantum circuits goes as follows. You have your circuit and you just look at it, and if you're hand optimizing or machine optimizing this thing, you start to look through this thing and find gate identities that you know. Okay, so here's an example of a gate identity. If I have two of these things, which are H gates, and this thing's called a C0 gate, then these can kind of trade places with each other. And when that happens, the C0 gate flips around. Okay, so that's just a rule that these gates satisfy. And another rule that these things satisfy is, now if I have a C0 followed by a C0, these things will cancel out. And then I get a simpler circuit. Okay, and these kinds of simplifications can actually, you can get a lot of mileage out of this. And you can list a few more of these things. So here's an example. But the problem with this approach is it's really unstructured. So you can just start listing these kinds of gate identities, and you can find some of these, and then you find a few more, and then you find a few more, and then you find a few more, and you find a few more, and you don't ever really know where to stop. I mean, it's just this kind of big space of gate identities, and there's no obvious discernible algebraic structure there. So a different thing you can do is take this circuit and break it down into something more basic. So these gates, you can kind of chop open and you get something more primitive underneath. And this more primitive thing is what we call a ZX diagram. And the things in this diagram are called spiders, or if you're from a particular kind of category theory community, you might know these things as something called commutative Frobenius algebras, but we just call these things spiders. Okay, so a spider, well, it's not really important actually for this talk how these things are interpreted, but they're just a certain kind of linear map, which is very useful for building diagrams. And they come in two flavors. So we have green spiders and we have red spiders. Or for colorblind people, we have light spiders and slightly darker spiders. And this little yellow box here is used to interchange the colors. Okay, so wrapping a green spider in this yellow box turns it into a red spider. Okay, and the useful thing about ZX diagrams, which circuits don't have, is that they're very flexible. They're so flexible, in fact, that I can just think of this thing effectively as just an undirected graph. So this corresponds to a certain linear map, but then if I deform this thing, say like this, then this corresponds to the same linear map, and this would correspond to the same linear map again. Okay, so the only relevant data in a ZX diagram is first this kind of list of inputs and outputs. Okay, so that's important. We sort of keep this ordering of inputs and outputs. But then the only important thing really is just the connectivity between these spiders. So the undirected graph, which describes how these spiders are connected to each other. And since we have this big undirected graph that's very interesting, then this is a good place to use graph rewriting. Okay, and the useful thing now that we have this much more flexible structure is all of these circuit rules get really subsumed in just a few more simple and kind of easier to remember rules about ZX diagrams. Okay, so this is, well, one of the versions of the ZX calculus, which is just a collection of, here we have 1, 2, 3, 4, 5, 6, 7, 8 rules. And these rules imply all of the hundreds of rules that I listed on the slides before. Okay, and in fact, this is actually complete. So if I draw two ZX diagrams, which represent the same computation semantically, then I can always translate one into the other one using these rules. Okay, so somehow this is already a maximal set of rules in terms of what you can prove with the ZX calculus. Okay, so I'll show this little toy example I had from before. So I had this circuit and I cut it open, and now I have some spiders. And now I can just start applying these rules. So what's the first thing I'm probably going to do is, if I have spiders of the same color, they can just fuse together. So nodes of the same color next to each other sort of fuse together into one node. And you can see that for instance, all of these green nodes along here fuse together, and then the little parameters on them add. These parameters are angles, so they add modulo 2 pi. And then as I go through and I apply some more of these rules, then what happens is I get a big simplification. And you can see that this circuit, which had a bunch of gates in it before, is actually fully classically described by just applying some ZX rules. I can see what this circuit did. In this case, I don't even need to run it on my quantum computer. Obviously, that's not always going to be the case, but here I've sort of totally chewed up this circuit using some ZX rules. Okay, so the question is, how do we scale up from that? So for doing by hand calculations, this is very nice. And we've been doing this for a long time now, probably 15 plus years. But to work with the kinds of circuits, even on these small, limited kinds of quantum computers that people are using today, we're really looking at ZX diagrams, which have something like 1,000 to 1,000,000 spiders in them. Okay, so that's the kind of scales we're looking at for today's computations. So obviously this is out of scope for doing things by hand. We need some kind of automation. So the first automated tool that we came up with, now I think this is well over a decade ago, was this tool called Quantumatic. And Quantumatic is described as a proof assistant for diagrammatic reasoning. And it's a sort of a general purpose tool. So you name some dots, like you say which colors of dots I want, and what are my rules, and then it has some sort of specific strategy language, which if you've ever worked with an interactive theorem prover, you probably recognize this kind of tactic type language, where you can implement some tactics in it and it will do rewriting for you. And I would say this is a general purpose but small scale tool for teaching and experimenting. I say small scale because it's not particularly good performance. It kind of starts to fall over if you have more than about 100 spiders in your diagrams. Just because the theory is very generic, so a lot of the algorithms are not very efficient. They're not really tuned to make use of the ZX specific structure. So at a medium scale is this tool. Well, actually, it's a Python library called PyZX. So PyZX or PyZX, which is like physics without the H in it. I would say this is a medium scale circuit optimization tool for the ZX calculus. So it's more specifically tuned to doing things with quantum circuits, whether it's optimizing or classically simulating, which I'll talk a little bit about later. And it's really specifically for doing things with the ZX calculus. And this can scale up to that thousands to hundreds of thousands regime pretty easily. Recently, we started wanting to do things that were harder than that. So either things with millions of gates in them, or just very hard kinds of computations on these smaller gates. So there's this new tool, which has showed up on GitHub just this year, called QuizX for quick PyZX. And it's an implementation in Rust of a sort of core functionality of PyZX. And then there's some bindings between these two things to make it more convenient to use. Okay, so I'll show a little bit of these tools kind of in a demo at the end. But the idea behind especially these second two things, and really all three of these things, is something that's very familiar to this community, which is to automate working with these diagrams. The first thing you should do is turn equations into directed rewrite rules. So you look at some sort of equational system, and you figure out which direction is really the direction of simplification, or the direction that you want to go in an automated way, and you just only allow your algorithm to apply rules in one direction. The other important thing to do in this automated regime is to focus on tractable fragments of this language. Okay, so one way you can prove completeness of the ZX calculus is there's a way that you can make unique normal forms, but these things are exponentially large, and they basically correspond just to the full exponentially large semantics of that thing, which is not really what you want. I mean, if we could do that, we wouldn't need quantum computers in the first place. So an important thing about this is we focus on certain subsets of the ZX language, which we can do things efficiently with. Okay, so one tractable fragment is the C0 circuits. Okay, so C0 circuits are just built from one kind of gate called a C0 or control not gate. And these things are efficient to classically simulate. In fact, they just correspond to linear maps on bit strings. And they're always equal to a circuit of polynomial size. So if I write some really long C0 circuit, that's always equivalent to something that's at most quadratically deep in its width. So you can already start to see that you can get some simplifications just by reducing to that smaller thing. And these correspond very neatly to a certain fragment of the ZX calculus, which is what we call the phase-free fragment. So this is where the spiders all have no parameters on them, or a no parameter is equal to an angle of 0. So that's called the phase-free ZX calculus. So that's an interesting subset to play around with. Algebraically very interesting. So if you've seen this line of work on interacting bialgebras and all this sort of stuff, graphical linear algebra, all of those structures are very similar or even the same as this fragment of the ZX calculus. Another interesting and probably much more quantumly relevant subset is what are called the Clifford circuits. Okay, so these are built using the C0 gate and two other gates. So one is the Hadamard gate, or this color changer thing that we saw before, and one is the S gate. So the S gate is a rotation by an angle of pi/2. Okay, so that corresponds to just some particular operation which is genuinely quantum. So that doesn't have a classical analog the way something like a controlled NOT gate would. Okay, but even though these things are somehow genuinely quantum, they're still efficient to classically simulate. So you can simulate a Clifford circuit in cubic time, thanks to this famous Gottesman-Nil theorem. So this is one of the kind of core theorems in quantum computing. And again, they're always equal to a circuit which is quadratically deep. So they also have this nice feature that if I have a very deep Clifford circuit, I can always bound that and make it smaller. And these are expressible by another quite tidy fragment of ZX calculus, which are called the Clifford ZX diagrams. Okay, so before these things were labeled by any kind of angle you could imagine. So there's a sort of continuously many generic ZX diagrams, but the Clifford ZX diagrams are always integer multiples of pi/2. Okay, so that there's only countably many Clifford ZX diagrams as opposed to the universal ones. And they're finitely generated. So they're generated by the phase-free things and also by this S gate, this pi/2 thing. Well, actually, yeah, you need both of these things to generate it. Okay, and the Clifford ZX diagrams also come with a simpler calculus called the Clifford ZX calculus. And this thing is also complete. So this thing is complete for Clifford ZX diagrams. So here we have what, 1, 2, 3, 4, 5, 6, 7 rules. And if you're looking at this thing as a non-expert, you would probably say this looks about as simple as the thing that I showed you before. But there was a bit of complexity hiding in this last rule in the universal case, and that you really had to do some trig to do some angle calculations here. And that's gone. That's just replaced by this simpler thing. And it's still complete, but now for this limited fragment of the ZX calculus. Okay, so now I'll look at this thing and think about how to turn this thing into a rewrite system that I can work with automatically. This might be a good chance to pause for a moment if anybody has any questions. Does anybody have any questions about what I've said so far?
Doesn't seem to be the case yet. So.
Okay, I'll just carry on then. You can feel free to interrupt me if anything is confusing as I go. Okay, so we have this equational theory, and it's clear with a lot of these rules what I should do to make them into simplifications. Okay, so these fusion rules where two things fuse into one thing. Oops, yeah. These fusion rules where two things fuse into one thing, it's kind of clear that that's the direction that I should simplify. I always want fewer dots, so I'll just fuse these dots together. And here, if I have a dot with one leg in and one leg out, then this is trivial, and this becomes just a wire. So this is also a simplification. But now something that puzzled us for a long time was this rule. So this thing is called the strong complementarity rule, this thing on the bottom in the center. And to give you an idea of how long this has been puzzling us, I basically wrote my master's thesis about how poorly behaved this rule is. So it's really, particularly if you see this as a rule going from the right to the left, well, for one thing, it's not confluent, but somehow it's worse than that you even get these bigger and bigger cycles of non-confluence. So it's very ill-behaved if I want to rewrite from the right to the left. We kind of realized later, and also in reading the interacting bialgebra stuff of some of the people here and Sobocinski and so on, that this rule actually really wants to go from the left to the right. So even though you actually have more dots here, this is somehow closer to a normal form than this thing is. Okay, but this can also give you problems, because if I treat everything as undirected, then I can actually apply the left-hand side of this rule to the right-hand side of this rule. So this wreaks havoc on termination. Because really all I need here is a red dot connected to any green dot, which of course there's loads over here. But something I can do to fix this is I just extend the context a little bit. So if I put a row of greens at my input, and I put a row of reds at my output, then this thing is already somehow done, but here I can fuse. So I'll just fuse those things together. And now what I've accomplished is I've actually managed to delete two spiders from my rule. Okay, so I've lost two dots. Sure, I've gained a bunch of edges, but I've lost two dots. Okay, so this thing is always going to terminate. And this actually works pretty well as a rewrite rule, and will take you to not really to normal forms, but at least to pseudo-normal forms. So very reduced things, which are easy to reason about.
Sorry, I actually do have a question on this, maybe because it's a good opportunity while the rules are still sort of on a slide.
Yep.
So from the viewpoint of some sort of double push-out writing, which we are usually taking here in this community, is it a correct observation that somehow some type of typed undirected graph writing where you always have sort of a predefined sort of interface say inputs and outputs that stay absolutely fixed? I mean, it seems like you sort of take a bunch of a diagram delineated by its boundary points, and then you just seem to completely replace the interior in most of these cases with some other motive. Is that about the right observation?
Yeah, that's the right way to think about it. So the rewriting here is always of graphs with interface. So earlier when I was saying kind of informally that it's important that I keep these input and output wires and even their order, or at least their kind of unique identities fixed, then that's the sort of pre-associated interface of this thing. And then I'm always rewriting in a way that respects that interface. So if I have something with 5 wires in and 5 wires out, and I do any kinds of rewrites, by the time I'm done, it will still be that same type of thing.
And maybe just a second question. So the difference to ordinary DPO writing is this particularly, I mean, not realizable additional constraint that the order of these points you choose must be fixed. I mean, for the input and output, you cannot, this is not up to isomorphism. You want to keep these particular points intact, so to speak.
Yes, yeah, you really want to keep them intact. So the order itself is not important, but the fact that these things have distinct identities, right? So I have some 5 qubits. Maybe I want to call them A, B, C, D, E, and these should really stay fixed. Because if I'm doing something with my first qubit, that's different from doing something with my second qubit. These correspond to different computations.
But the identity comes from the host graph, and you see this as a rewrite rule. The moment you match, you get the identity essentially. So you wouldn't actually, I mean, you could do ordinary DPO rewriting with this in principle, no? Or what goes wrong? Oh, sorry, maybe you are going to say this later in the talk. Yeah, but.
No, I mean, you can essentially, yes, I think you can do ordinary DPO rewriting in this kind of case, but you still want to do this extra bit of bookkeeping, I think, to at least remember which things were your inputs and outputs, and which inputs and outputs those correspond to. Just like if I have a register of bits, I want to remember what my first bit was and my last bit was, and so on.
Very interesting. Yeah, I might ask you some more questions later. So, but sorry, I didn't want to interrupt the flow.
Yeah. This might actually be a nice moment to show that this does work fairly well. Okay, so here's this rewrite system that we have so far, and maybe I'll just jump over to the tool. Let's see. Okay, is this visible now that I've changed over? You can see some what looks like some Python code. Okay, so here's the interface to PhysiX, which is a Jupyter notebook. It's just a particular way of running little bits of Python code and getting some outputs. Okay, so here it's called Chasm, which is this kind of assembly language for circuits. It's a very simple little language. This thing means do a C0, and this means do a C0 between the 0th and the first qubit, and so on. So here I've just written a little circuit with, this means it has 4 qubits, and then just done some C0s. Now I can save that into PhysiX, and I can draw it. It looks like this. Okay, so here's a circuit with some C0s. And I've told it to give me some labels so that I can refer to the dots in this thing. Okay, so even though this thing looks like a circuit, it's actually a graph. And these little nodes can actually move around. So this is a graph. And if I wanted to do something to this graph, well, the simplest way I can do something to it is I can just call a function on it to mutate the graph. So one thing, this graph is called G. I can fuse. Let's for instance, let's fuse this node 4 with this node 6. Okay, it says true, which means actually that rule matched there, and then it applied it. And then if I draw this thing, you'll see that indeed these two nodes have been fused. Okay, so a kind of useful thing about this thing returning true when it matches, and so if I put say 4 and 9, it should return false. So if it doesn't match, it just returns false, and it's a no op on that thing. So a useful thing about that is I can use some kind of some nice Python code writing patterns. So I can wrap that thing. For instance, I can say any. And let's see, if I fuse G with G dot edge source E G dot edge target E. Let me get my brackets right. For E in G dot edges. Okay, so this anything is basically like a big OR, right? It's ORing over all of the for E in edges. And then the first time something returns true, it's just going to do it and it's going to exit. So if I do that, and let me draw it again, I'll see that something fused, and if I do it again, I'll see that something is fused again, and so on. Or I can just wrap this thing in a loop. So if I say something like while this pass, then it will fuse as much as possible on my graph. Okay, so I mean, there's better ways to do this, and kind of slicker ways to interact with this tool interactively, but this is a very simple way. I can do some rewriting with this library. So yeah, here's well, essentially just in a single little block, the thing I just showed. Okay, so I can do a slightly more elaborate thing, which I've called phase-free simp, which is effectively doing these rules as much as possible. So remember, I started with this C0 circuit, which looked like this. And now if I apply this thing, I'm telling a little bit of a white lie about what it's doing, but not much of one. If I apply this thing, it will terminate very quickly, and it gives me something that looks like this. Okay, and this is a nice pseudo-normal form, and actually for these particular kinds of reversible maps, this thing is unique. So a nice normal form for these C0 circuits. And a nice feature of these normal forms, oops, there's my slides. A nice feature of these normal forms is you can actually read off how it corresponds to a linear map. Okay, so this is a linear map on bits. And here's my sort of bit vector x0, x1, x2, x3. And what this linear map does, I can read it off of the graph. So it sends this 4 vector to this 4 vector. And you see this first output was x0 plus x2 plus x3. And I can see where those things came from. It's just the edges that are present in this graph. So here's an edge from this output to x0 and to x2 and to x3. Okay, so these normal forms are very nicely connected to the semantics of these things. So that's kind of cute, and it's useful for this phase-free fragment. But to do some more non-trivial stuff, we really need to cope with these 2 different colors. So really with this color change rule and with this other rule, which I haven't really said much about so far. So the first thing we can do, we can look at this rule and realize that, well, since I can always freely interconvert between red and green, why don't I just make everything green? Okay, so that's something I could do. I can cut my troubles in half by just making all of my dots green and only deal with green dots from now on. Okay, so if I have a diagram like this, I can turn all my red dots into green dots, and then do a bit of syntactic sugar, which actually goes into our graph representation a bit, which is that if I have one of these wires and it's got a Hadamard gate on it, I'll just represent that as a different kind of edge type. Okay, so we have normal edges, which are just like these things, and we have these Hadamard edges, which I'll just draw as a kind of blue dashed edge. Okay, so So I've just changed from being an undirected graph with two different kinds of nodes and one type of edge. Now I've got an undirected graph with one type of node and two different kinds of edges. Okay, so the complexity is sort of the same. And these things are a bit easier to work with. So if I keep massaging these rules using that trick, well, this thing becomes a simplification, right? Because I don't want any red dots anymore. So I'll just make a rule that rewrites them into green dots in this kind of way. And now I don't want to introduce any more non-confluence than I have to. So I'm going to actually make these things not refer to red dots anymore. Okay, so if I got rid of my red dot, that's going to block these rules from applying. So I should fix that up. So here, all I've done is I've changed the red dots to green dots surrounded by these dashed edges. Okay, so now this is effectively the same system. But what will happen is first well, maybe I'll fuse some red dots, but actually that doesn't matter anymore. I'll just get rid of all my red dots and I'll work with these three rules kind of from then on. Okay. And now this thing I can sort of, it's clear that I should simplify it this way. And there's actually a kind of a nice generalization of this rule, which looks like that. Okay, so kind of a lot happened there. Really what happened is I generalized this rule and that rule. But these things were already familiar in the quantum computing literature. This thing is called pivoting, and this thing is called local complementation. Okay, so these are kinds of graph theoretic transformations that were already getting used quite a bit in what's called measurement-based quantum computing. But here it's kind of clear what these things are buying me. So here, if I have a pair of nodes and they have sort of integer multiples of pi angles on them, then I can delete them and I can introduce edges between all their neighbors. Here, if I have a single node with a plus or minus pi by 2, I can delete it and introduce a complete graph of all of its neighbors. Okay, so both of these things let me delete nodes. They're nice, well-behaved simplifications. Again, not confluent, but again, it will take me to a fairly nice pseudo-normal form that's easy to work with. And using this system, so the system that I showed you here, we can do something which is called computing the skeleton of a circuit. Okay, so these things, those rules I showed you before will totally chew up anything that has a pi by 2 multiple phase in it. So if I give it a generic circuit, it'll just eat up all of what's called the Clifford part of the circuit and just leave behind the hard stuff. So here you see I've got these pi by 4 phases left behind, and also some kind of connectivity which says how they're related to each other. Okay, so this skeleton is a kind of a useful artifact to work with when you're thinking about circuits, because they capture somehow the genuine quantumness, right? So this is the stuff that I can't do classically. This is really what I need a quantum computer for. But now this thing, I said I wanted to do circuit optimization. So I want a big circuit, and the thing that should come out at the end is a little circuit, because at the end of the day, it's circuits that I want to run on my quantum computer, not ZX diagrams. Okay, so how do I get a circuit back out of this very reduced skeleton thing? Well, this is a kind of a subtle and interesting story. So one thing to realize is that ZX diagrams can represent any linear map, but circuits are always unitary, which means that there could be ZX diagrams which don't even correspond to circuits at all. And in fact, I think even when it does correspond to a circuit, it's a non-trivial problem getting a circuit back out of it. Okay, so this is what I call the circuit extraction problem. Given a ZX diagram, which represents a unitary, so maybe it came from a quantum circuit, find an equivalent circuit. And maybe it should say something like with polynomial overhead or something, because if you can just sort of compute the whole exponentially large matrix, then this is very easy. And now, okay, maybe this doesn't mean much to this kind of community, but I would conjecture that if you can solve this in general, so for an arbitrary such diagram, then this implies some complexity theoretic nonsense. So basically that these two complexity classes collapse into each other, which is very unlikely to be true, I would say. So this post BQP is actually the same size as P space. So it's a very massive class, which is, whereas these are the things that you can do efficiently on a quantum computer. Okay, so rather than telling us that this is hopeless, what you should get from this is you need some heuristics or at least some extra information to be able to get a circuit back out of a ZX diagram. Okay, well, if this is indeed true. Okay, so here's a, well, first I'll give it as kind of a heuristic. Okay, so if I have this thing, so this is a ZX diagram, which doesn't look much like a circuit, I can start from the, let's say start from the outputs, but this would also work if I start from the inputs. Start from the outputs and just start pulling gates off of here. So when I see something which looks like a quantum gate, I'll just pull it out of this diagram. And if I can pull everything out of the diagram like this as gates, then I'm done. Okay, so these dashed edges, these things look like Hadamard gates, so I'll just pull them out as Hadamard gates. Okay, and now I'll draw a little box around how far I've made it. I call this thing the frontier. I call this the frontier, which we sort of want to push the frontier all the way to the left. Now these things, I can do a bit of spider fusion and I can pull these things off. And these are quantum gates. These are called quantum phase gates. And I can build these quite easily out of the gates I know about. And now, so what am I doing here? I'm probably going to pull out some more Hadamard gates. So these blue edges will come out as some more Hadamard gates. And now I think, yeah, I can pull out the pi gates. And now I can pull out another, no, what am I doing here? So now at this point, I'm kind of stuck. And the reason for that is I get a kind of a cycle. So here I have a cycle and it's not really clear what to do next. I think, I mean, I could have pulled these out, but I didn't in this example. So what you can actually do is I can look at this thing. So I can now look at the biadjacency matrix of my frontier with my unextracted stuff. So the things to the left of my frontier. So here I've just written that connectivity. And a kind of curious thing that you can do, that you can prove using the ZX rules, is that if I do a controlled NOT gate after my frontier, it will apply a primitive row operation to that biadjacency matrix. Okay, so this is just something you can prove using the ZX rules. So if I do a CNOT gate here, then this has changed the edges here. And what it's done is it's applied a primitive row operation to that adjacency matrix. So it's added the fourth row to the first row, okay, by putting a CNOT between the first row and the fourth row like this. Okay, so that means that I can use CNOT gates effectively to do Gaussian elimination on this biadjacency matrix. And if I get lucky, I can eliminate this until it's a point where it's kind of obvious how to proceed. And I can sort of pull out some more gates and then Gaussian eliminate some more and pull out some more gates and so on. Okay, and this works. And actually, initially, we just coded this up and we were very surprised to find that this just works all of the time. Okay, so there's no reason that this would have to work. In fact, we're doing Gaussian elimination on matrices that are very short and very wide. There's no reason that these would always get unit vectors on their rows. And having a unit vector sort of means that you can make progress. So we had to sit and sort of, this was a case of we wrote the code and then we had to figure out why it was working later on. And it turns out the reason why this was working has to do with something called G-flow or generalized flow. Okay, so G-flow is a property of undirected graphs. It's also been around for a while in a certain literature or measurement-based quantum computing. And well, for the purposes of this talk, it's just a property of graphs. Okay, I have a graph and there exists some ordering and there exists some function G from nodes to power set of nodes, which satisfies some stuff. Okay, so this is the stuff that those pieces of data satisfy. The important thing is that it's non-trivial. So not all graphs have a G-flow. But quantum circuits in particular have a G-flow. So these things, these ZX diagrams I get by sort of cutting open my gates and then I have a diagram, those things have a G-flow. That's easy to show. What's harder to show, but actually not too bad, is that all of these rules preserve a G-flow. And in fact, if your graph has a G-flow, that extraction heuristic that I showed you on the last page always works. So because I start with something that has a G-flow and then I preserve that invariant with all of my rewrites, my heuristic works. Okay, so I can always extract and I can get a circuit back out. Okay, so now there's a kind of evident workflow I can use for optimizing circuits. I can take my circuit, I can apply all of my reduction rules to get a very small thing, and then I can try to extract a circuit back out of this. Okay, and that's our kind of basic framework with some variations, which we've built some other stuff on top of. Okay, so that's the kind of methodology we've been using for optimizing circuits. The first thing we applied this to was something called T-count reduction. Okay, so I introduced Clifford circuits before. A little tweak to Clifford circuits are called Clifford plus T circuits. And if you were sleepy before, the only thing that's changed here is that there's a pi/4 here now rather than a pi/2. Okay, so this actually makes a huge difference. Okay, so it still has the Clifford circuits because if I just square this thing, then I get my pi/2 thing back. But it's actually universal for quantum computation. So Clifford circuits were efficient to simulate on a classical computer. These things are universal. So it means they're very unlikely to be efficient to classically simulate. And yeah, universal just means that I can approximate any quantum operation to arbitrary precision just using these three gates. Okay, again, a kind of a famous result in quantum computing. Okay, and since they're universal, we would hope they're not efficient to classically simulate. Otherwise, you know, Google and everybody else is just wasting their time building quantum computers. Okay, so T-count reduction has to do with reducing these T gates. So somehow the T gates are the hard stuff in these quantum circuits. And there's a lot of reasons why you might want to do this. One of them is that thinking kind of way ahead into the future, and we want to implement these quantum circuits in big fault-tolerant kinds of ways. The Clifford stuff is easy. So like these C0 gates and the Hadamards, they're easy to do, and the T gates are about 100 times more difficult. So there's just particular schemes. So there's this thing called magic state distillation, which you use to realize T gates, and it's just very inefficient. So you actually want to get rid of as many T gates as possible because they're just hard work to do in these kinds of schemes. Okay, so here was our basic schema. We take some circuit and then we compute its skeleton, and in the process we've eliminated some T gates and then we extract the thing back out. Okay, so here I think in this particular example there's something like 15 T gates here and there's eight T gates there. So you do make some savings in doing this because things cancel kind of along the way. So we did this in 2019 and it worked out pretty well. Compared to the things that were around at the time, this was matching the kind of best techniques that were around, at least for this ancilla-free T-count reduction. And for a lot of cases, it was just beating the things that were out there as well. So this looked quite good. We were very excited about that. As usual in this kind of area, about a month later, this other group came out and they had some other thing that was done in a totally different way, but exactly matched all of our statistics. And people from the quantum computing community would say, well, the thing that Zhang and Qin did was much easier to understand than all this ZX business. So what's the big deal? But this is ongoing, and there's been some more progress on the ZX front, and some new results that have kind of gotten ahead of the state of the art again, and also done things more efficiently than the state of the art. But that's kind of the summary of that. Something that's more relevant to now, so the things that people actually care about now rather than a long time in the future. So those T-gates were sort of about these fault tolerant schemes, which we won't have for, I don't know, 5 to 10 years or something, at least. Something relevant now is 2-qubit gate reduction. So 2-qubit gates are, in general, about 10 times as hard to implement as single-qubit gates, for a lot of reasons having to do with the physics of how these quantum computers work. So 2-qubit gates are just a lot more noisy, and you get crosstalk and leakage into higher energy states and blah, blah, blah. So actually, if you talk to somebody who's trying to do stuff on a quantum computer today, what they want to do is get rid of as many of these as possible. That's kind of problem numero uno. So we've been thinking about this lately as well. And also within this kind of paradigm of taking a quantum circuit and computing its skeleton. And an interesting thing we can do there is that these skeletons are not unique. Okay, so this is at best a kind of a pseudo-normal form, but there's a lot of kind of non-trivial congruences on the skeleton. And the thing that happens is if I rewrite this to another equivalent skeleton, it actually extracts differently. Okay, and you can actually get drastically different 2-qubit gate counts depending on which equivalent version of the skeleton you have here. Okay, so you can start to play around with this using classical optimization approaches. So the simplest thing we did is we took the C0 count of our extracted circuit as a cost function. We did simulated annealing just by randomly applying rewrite rules to the skeleton and then extracting it and seeing if you sort of made progress or not, and then just annealed with that, which is a very, very sort of textbook way that you can do classical optimization. And this also works pretty well. On smaller circuits, it actually works very well. So let me find a good example here. So here, this mod 5.4 circuit started with 63 gates, and by the time we were done, it had 14 gates. And the things it's sitting next to, so these are kind of state-of-the-art compilers. This is Cambridge Quantum Computing's one. This is IBM's one, and it's actually doing a lot better than those guys. But the problem is this search space is actually quite elaborate, and scaling up is a bit of a work in progress. So we get good behavior even sometimes up to about 15 qubits, and we're trying to push that farther. But maybe we need some more expertise in machine optimization, machine learning to come into this problem to help us out with it. So here's a question, at least about that first thing, that gets asked a lot. So if you spend a lot of time working on reducing the T count, you hear a certain kind of critic say, "Who cares?" Because these fault tolerant quantum computers are so far in the future that nobody actually cares about T count anyway. But one reason it does matter has to do with classical simulation. Okay, so you can simulate things better and faster if you can reduce T counts of circuits. And I mean, there's lots of interesting things you can do just by simulating quantum circuits. For instance, you can do simulation of chemical reactions, quantum chemistry, and this kind of thing on classical supercomputers if you can simulate quantum circuits better. Okay, so this is a hard problem in general. Like everything in complexity theory, we don't actually know how hard it is. But all known algorithms are exponentially hard in some measure of how big quantum circuits are. Okay, so the naive thing is it's exponential in the number of qubits. It takes exponential space in the number of qubits just to do naive simulation. There's sort of other things which simulate, which go exponential in the tree width of the circuit. These things are based on what are called tensor networks. But interesting for us is there's these stabilizer decomposition techniques, which go exponential only in the T count. So I can have circuits which are very wide and very deep, but if they don't have so many T gates, they're actually easy to classically simulate. So that's kind of cool. So we were wondering, because we had these cool T count tools, if we could play around with those techniques. Okay, and the way these things work is they simulate a hard circuit by summing over lots of easy circuits. And I put lots in all caps because this is like exponentially many easy circuits. But you know, it's kind of whether it's exponential with a little e or a big E exponential is really the question here. Okay, so they rely on this thing called stabilizer rank, which actually I don't really need to go much into details here. But basically, if I have a quantum circuit, I can decompose it as a sum of easier things. This is actually a state. I can decompose it as a sum of easier states, which are called stabilizer states. And if this n, so if this sum is not too big, then this is not too hard. It doesn't take too long. Okay, and well, this is just saying the Gottesman-Kenil theorem, which I referred to before, means that I can simulate this thing, which in particular I can compute what are called amplitudes in n times polynomial time. So actually finding good stabilizer decompositions gives you fast classical simulation. Okay, so again, this is a hard problem in general, but there's some upper bounds on how to do this. So the naive thing I can do is I can just decompose T gates into 2 terms each. So don't worry so much about the mathematical details here. The important thing is doing the naive thing gives me 2 to the T many terms, where T was my number of T gates. But there's actually a less naive thing, which is this big mess. And again, don't worry about it. But this less naive thing is I take a chunk of 6 T gates and I decompose it as 7 terms. Okay, so that kind of sounds like you're doing the same thing. And it does, in some sense, scale the same way. It's still exponential in its scaling, but it scales as 7 to the n over 6 rather than as 2 to the n. So 7 to the n over 6 is like 2 to the 0.4 T. Okay, so passing from this thing to this thing means I can simulate circuits which are about twice as big doing this not naive stuff. Okay, so we translated this kind of less naive decomposition into ZX diagrams, which was fun, at least to see that, you know, this is less poison to the eyes than this thing on the previous page. But more interestingly is that now that we have these things as ZX diagrams, we can start mixing decomposition with simplification. Okay, so we can decompose stuff and we can simplify some and decompose some more and so on, and see if this gives us some traction, classical simulation. Okay, so why? So if I do my sort of naive decomposition, so here say I have 33 T gates to start with, well, I'll get a bunch of terms which all have 27 T gates. And then each of those gives me a bunch of terms which all have 21 T gates, and so on. Well, if I actually interleave this with some simplification, then I can save myself a lot of work. So every time I get rid of 1 T gate, I'm saving myself kind of exponentially much work down this tree. And this does actually work. This does actually work very well. So in some cases. So I'll just show maybe my last little bit of demo here. So let's see if I can make that a bit bigger. Hopefully this will look good. Is that visible? Is this text visible?
Yes, that's looking good.
Okay. So here I'm simulating what's called a hidden shift circuit. So this is solving a particular quantum algorithm called the hidden shift algorithm using the stabilizer rank decomposition. Has 50 qubits. It has 12 what are called CCZ gates per oracle. Basically what this amounts to is that this number controls how many T gates there are, which I'll show you at the end. And then this is just a random seed, so that I know this thing will finish in a reasonably short amount of time. So I'll just run that. And now what it's doing is it's simulating measurement outcomes for each of those qubits going out. So it's thinking, okay, and now it's done. So if I go up to the top, oops, so each of these qubits is getting simulated, and here is the sort of T count that I'm starting with. So I form my simulation job, and then I reduce it with my simplifier, and this is the T count that I start with, and then I start decomposing and reducing sort of greedily as I go. And you see in a lot of these cases, I actually managed to kill all of my T gates right at the beginning. In some of these cases, I have 14, 28, something like this. And these things are simulated fairly easily. Like this is probably the longest one. It takes like little over a second. Here's the shift. So in this hidden shift, I have to hide a bit string called the shift. And there's the shift I hid in there. And here's the simulated measurement outcome. So you see that it works. And I simulated this circuit. So it had 50 qubits. It had a T count of 168. It was done in 8.7 seconds by summing 490 terms. Okay, so if I did this naively, well, even the less naive approach, so that second thing, this would have something like 10 to the 50, 10 to the 49 terms. So you know, this would be totally impossible to do even on a supercomputer. Okay. So this can really make have a big impact. And I think with that, that's more or less what I wanted to say. So this is the framework paper, graph theoretic simplification with ZX calculus by Ross Duncan, Deirdre, myself, and John Van Vetering. Here's the T-count paper and some GitHub links to these things. The CNOT stuff and the classical simulation stuff is coming out very soon. So keep an eye out for those things. And with that, I think that's what I want to say. And thanks. Happy to answer questions.
Thank you very much, Aleks. So maybe can I unmute and clap, which is so people. Yeah. So do we have any questions for Aleks? Maybe just unmute yourself if you do.
Well, if I may I, Nicholas?
Please.
No, I'm just a curiosity. Aleks, have you checked what happened if you consider just a category of graphs satisfying G-flow? Do they have some nice property categorically?
Oh, I see. So you take the you just take the subcategory of graphs where the graphs satisfy G-flow, and so G-flow is a structure, not a property, but you can always say there exists some G-flow, and then it becomes a property. Does this thing I mean, so the short answer is no. I haven't considered that. Does that have any interesting properties? It's closed under certain graph theoretic operations, and that's kind of the key to this idea that these rewrite rules preserve the G flow. So you can find rewrite systems where this category is closed under them. But yeah, I don't know. That might be an interesting thing to look at, see if there's any kind of categorical handle on that.
Okay, well, you know the usual, right? Push out, pull back.
Yeah, I wonder if. Yeah, I mean, there's a lot of very simple questions you could ask about it. So, for instance, does this category even have products? And I don't know. There's sort of an evident way that you could try to lift G flows to say like products graphs or something. Simon might know these things already, or various other people who spend a lot of time thinking about these things. I would be surprised if it had push outs, let's say. So it's not a very compositional. Well, it's compositional in some ways. So it's well behaved if I take two things with G flow and I glue all of the outputs to all of the inputs of the other thing, then the resulting thing will have G flow. But if I sort of tried to glue them sideways or something like that, then it probably goes wrong.
Right, and I think we have a question by Hans-Jörg. He is raising his hand.
Yeah, okay. Yeah, thanks, Aleks, for this enlightening talk. I have the question, you have the two levels, circuits on one hand and ZX diagrams on the other hand. Then you go from the circuits to the ZX diagrams, can do a lot of nice optimization and simplification, but then the way back to the circuits is hard to do. Mm-hmm. Why cannot all the simplification be done on the circuit level directly?
So you can do a lot of things at the circuit level, but it's a bit less structured there. So for instance, I was showing those slides before of these pages and pages and pages of gate identities. So those were all happening purely at the circuit level. There are also techniques where you can do ZX type rewriting, where you're actually preserving all the time that you have a circuit. And the drawback of that is you sort of limit yourself in the kinds of the sorts of rules you can apply. So there's only kind of a handful of rules have this kind of property. So what's actually more useful sometimes is to kind of go out of the circuit world and go back in. So kind of a useful analog, I think, to this is like complex numbers. So if you think, well, I actually only really care about real numbers, but certain calculations are a lot easier if I sort of go back, if I go sort of via the complexes and then back to real numbers at the end. I think of ZX diagrams as kind of like that, this kind of imaginary but easier to work with structure, which sort of encompasses circuits.
Okay, in particular, this means on the ZX level, you have these 8 rules that are complete. Mm-hmm. And you have nothing like this on the circuit level, I understand.
For any universal family of circuits, that's right. Nothing like that exists.
Yeah.
So
it would help to find such a set of universal rules.
Yeah. So this has been done for Clifford circuits.
Okay.
And it's been done for Clifford plus T circuits, but only up to 2 qubits. So it's very limited.
I see. Okay. Thanks.
But I think if it did exist, it'd be very long. It might even, you know, sort of fill a book once you have all the rules there.
So may I ask one question?
Yes, please.
Alex, just a curiosity from an outsider of the world of quantum software and quantum computing. Okay, if we think, just to understand how far we still are from a real use of quantum computing or concrete interesting things. Just an intuition, for the famous algorithm for factorization in prime numbers, for a medium-sized number, how many qubits you need?
Yeah, so there's an interesting line of work which started with a really big number, and it's been slowly working its way down. But to do a factorization, and this is also with error correction, so that it will actually work. To factorize a number which is too big to do on a classical computer, it's still on the order of millions of qubits that you need to do that. I mean, I think it used to be hundreds of millions, and then they figured out better things to do, and then it was tens of millions, and then now it's more like around a million, if I want to say right. And this is kind of an active ongoing thing to try to get this sort of to try to get what we have and this number to sort of get closer to each other from above and below.
Okay. So in the algorithm, because I don't know precisely which is the use of the qubits in the algorithm, but the idea is that you need a number of qubits which is in a sense proportional to the size of the number, or you can reduce the computation by sophisticated techniques in order to use less qubits.
Well, no. So the number of logical qubits. So you have this idea of logical qubits and physical qubits. So the number of logical qubits just depends on the size of the number that you want to factorize. The number of physical qubits, so this is where I take my logical qubits and I add error correction to them, and now I encode them as many qubits. This is where all the overhead comes from. Okay. So the logical qubits, you need, I don't know, a couple of hundred or something. And then the error correction blows this number up from a couple of hundred to millions.
Okay, thanks. So this
and then it's getting that part better, which people are sort of spending the majority of their effort on, I would say.
So there's still a long way. So
it's from what we know now, it looks like it's still a long way off.
And I had another question which was very close to the one by Hans-Jörg. So the precise relationship between these amount of circuit identities that you've shown on the various papers and the equational theory of the ZIX calculus. So the completeness of ZIX implies that all these identities basically hold for the ZIX calculus. So if you translate the two circuits of any of those equations, you get equivalent ZIX circuits, right?
Yeah, that's right.
And the suspect is that there are more and more circuit identities that are also valid, so the way these identities have been developed is because of I guess improving the possibility of simplifying. So GReTA, larger and larger circuits can be equated.
Yeah, so I mean the things I showed was a sort of a random selection, and I feel kind of bad because there's a particular group of people doing great work at Dalhousie, which I kind of pick on because they put all of their circuit identities together, so it's very easy to stick these up on a slide. But what you normally see in in that kind of work is that you still have a relatively small number of identities which suffice to prove everything. So for instance, with Clifford circuits, there's something like 10 or 13 rules which can prove everything. But then to get a rewrite system with nice properties, they spin that out into hundreds of rules, which are derived rules from those 10 or 13 identities. And this is really to get something which is, say, terminating and confluent and gives them nice normal forms and so on.
Okay, thank you very much.
So it's actually following up on this particular line of questioning, because we saw this talk by Pavel on your work with the string diagram rewriting, or more like this rewriting with Frobenius, I think it was called also. So when you're saying you have these derived rules, so I'm assuming something special is going on here, because you have these interface preserving rules. Yes. So I guess if you start plugging them together, I mean, is there any interesting compositional structure here on sort of these compositions of rules themselves versus just executing it on a particular problem? I mean, do you do learning, for example, on sequences of rewrites that are more optimal than others, or have a better chance to simplify? Because I asked you this last time already. Sorry.
Yeah. I mean, that's not something that's been explored too much. There is some nice two categorical structure of these things. Because you can form these categories of co-spans, and then you can see rewrites as two cells there. And you can think about, well, you know, if I have a rule, then I can form a derived rule, say by gluing some more context onto the outside of it.
Yeah, but you could also do a derived rule by actually composing the rules. Yes. So
yeah, I see what you mean, like temporal composition, like this tracelet style things.
Tracelet style, but I mean, so the question is really, because you have such an interesting application field, if there's anything we can contribute from the community, I mean, if there's any hope or intuition at least, I mean, the thing we do is more on the end of concurrency theorem and these sort of things. So because I mean, it seems like the moment you start composing rules, you don't pay at least directly the price of acting on a million vertex graph. Yes. So I mean, at least maybe if there's some structure to be learned, it's more in these sequences than in the concrete example you use. But do you have any intuition? I mean, maybe it's the wrong question, but
I mean, it might help you. It might help you exploring these spaces a bit better. Yeah. So for instance, the CNOT thing I was talking about, where you're doing some simulated annealing. There, I mean, in general, you have these very deep rewrite sequences where there's a bunch of effectively random rule applications, and then a very costly process to compute the cost function of applying those rules, because you have to apply your rule, and then you have to extract the whole circuit to see if that helped you or not. And there may be some kind of compositional thing you could do to try to short circuit that. And do it.
And the other question was, in this G-flow setting, which you said not every year. Was it correct that every circuit has this G-flow structure, or you can put it on?
Every circuit it in fact has something that's stronger than G-flow, which is just called flow. So right. So it's like without the G means generalized flow.
And so is there anything known about properties of such flow under transformation of admissible rules? Is there any, sorry, I think that's pretty much what Hans-Jörg asked. But I mean, is there any, at least the rules you showed seem to be few. Do they have a definite effect on G-flow?
Yeah, so there's, all of those rules preserve the G-flow. And as I said, this G-flow is a kind of a structure. So it's really a particular ordering in this function from a node to a set of nodes.
Very interesting.
And you can actually compute the updates to this structure. I mean, this is effectively how you prove that you preserve the G-flows. You compute how the G-flow should be updated for the new graph based on the old graph and the old G-flow. And yeah, particularly these local complementation and pivoting rules, which are really the non-trivial stuff. They preserve the G-flow, and it's non-trivial to show this.
Yeah, so maybe if you could send us some references on these G-flow things, and on maybe if there's any work at all on these sort of ensembles of rewrite steps, that could be a nice direction. Yeah.
Yeah. So I mean, the place to start probably with the G-flow is just this graph theoretic simplification paper.
Oh yeah. Oh, very good.
But yeah, I mean, there's a lot of literature on this also in graph theory, because there were things when people were thinking about sort of field weighted graphs whose edges are weighted by field elements and stuff. All this stuff like local complementation and stuff was predating the quantum things.
Right.
Sort of.
I'm asking also because our colleagues from the algorithmic chemoinformatics teams, they have this technique called integer hyperflow, and that is more direct to find sequence of rules that satisfy a certain objective. I'm just sort of would just be interesting to see if there's any objective function you can put on your circuits that behaves nicely enough that under rewrites, and that you can see whether a rule composition would decrease, for example, this function or not. Yeah. Yeah, it's just pure speculation. I mean, we should discuss in the work group at some point. Yeah, with Daniel and Jakob. Yeah. I mean,
this is especially this 2-qubit gate thing is very much still not a solved problem.
Oh yeah.
I think there's much more to do there, and it can be optimized much more, because you're also in not just with the normal form, but you're making many choices during the extraction as well. And if you make different choices, this can have a big effect on how efficient the circuit is when it comes out. And sometimes it can be very bad. So that's we're working on that.
Very interesting. So do we have any other questions? Sorry, I didn't want to talk all the time. Maybe just unmute or raise a hand if yes. Okay, so doesn't seem to be the case. So, I mean, Aleks, thank you very much. That was extremely interesting, and maybe hopefully see you around for some of the work groups. This sounds like something one should discuss a bit further. So, many thanks.
Okay, yeah, thanks for having me.
And yeah, and also thanks to everybody who participated today. And it's just to say that we will return with the GReTA series sometime, I think in the middle of September, if I remember this correctly. And so wish you all a very nice summer. And once again, Aleks, thanks a lot. And yeah, see you at the next time.
Bye-bye. Bye, Nicola.
Goodbye.